Hi guys, welcome to Simplified Education. In the last lecture we have discussed about the zeroth law of thermodynamics and the work energy interactions. Now I will discuss the heat transfer processes and I will calculate the heat energy for different thermodynamic processes. Next we will discuss the first law of thermodynamics. So coming to the heat energy interactions, or that is mainly heat transfer. So heat transfer is nothing, energy interaction by virtue of temperature difference is known as heat transfer. That means whenever there is a hot body and another one is cold body, so there is a temperature difference between those two bodies and heat is transferred from the higher temperature body to the lower temperature body. That is called as, that type of energy interaction is named as heat transfer. So coming to the heat transfer is directly proportional to the temperature difference. Increasing the temperature difference, the heat transfer will also increase, and it is also directly proportional to the mass of the body. Okay, so the heat transfer is equal to mc delta T. That means it is directly proportional to m, again proportional to temperature difference. So putting a constant of proportionality, we are getting Q equal to mc delta T, where C is a constant and which is also called as specific heat. Okay, so C is of two types. One is CV, another one is CP. Okay, CV is when the process is occurring at constant volume, we are taking CV, and when the process is occurred at constant pressure, we take specific heat at constant pressure, that is CP. Next, coming to the sign convention, as we have discussed in the work energy interactions, there is sign convention for work transfer. When work is done by the system, we take it positive. When work is done on the system, we take it negative. Similarly, for heat energy also, when heat is supplied to the system, okay, when heat is supplied to the system, we take it positive. Heat is supplied to the system, we take this as positive, and when heat is rejected from the system, then we take it as negative. So similarly, in case of work transfer, we have discussed about the surroundings. When heat is added to the surroundings, what will happen? When heat is rejected to the surroundings, what will happen? Okay, so when heat is heat supplied to the system means heat is rejected from the surrounding. So in both the cases, we can tell QE is equal to positive. So heat will be positive, the sign convention for heat transfer. So now I have taken one system where 10 kilojoule of, if 10 kilojoule of heat is added, that means heat supplied to the system will be positive plus 10 kilojoule. Heat rejected, if 10 kilojoule of heat is rejected by the system, then we take it as minus 10 kilojoule. Likewise, heat supplied by the surroundings will be plus 10 kilojoule. Why? Because heat is rejected by the system will be equivalent to the heat is supplied to the surroundings. So heat supplied to the system, this is equal to this. How? Heat supplied to the system means the heat will come from surrounding to the system. That's why both these cases it will be positive, and heat rejected by the system will be equal to heat supplied to the surrounding. Both are same, because when heat will be rejected by the system, it will go to the surrounding only. So in both the cases, this will be minus 10 kilojoule. Okay. Next, coming after the sign conventions, we will discuss the first law of thermodynamics. So coming to the first law of thermodynamics, it is an energy conservation law of thermodynamics. The statement which says the first law of thermodynamics is, for a closed system undergoing a cycle, the net heat transfer is equal to the net work transfer. Here 2 points you have to make. First one is closed system, next one is cycle. So these two are very important words in this statement, that is for a closed system and for a cycle the net heat transfer will be equal to the work transfer. I have also mentioned over here for the first law of thermodynamics, summation of Q equal to summation of W for what? For closed system and for cyclic. This cyclic process can be reversible or it can be irreversible, it can be anything, right? This is our first law of thermodynamics. Next, coming to the heat transfer properties. Heat transfer is a path function as it depends on the path. Okay, it is not a point function as it does not depend on not only on the initial and final points, it depends on the path through which heat is transferred. That's why it is a path function. To illustrate that, I am taking one diagram. There is a pressure and volume diagram. Suppose this is 1A2, this is 1A2 process, this is the first process in forward directions, and the backward direction process is 2B1, another backward direction process is 2C1. So this is different paths, right? So if I am telling heat is a path function, then heat for the path 2B1 will not be equal to 2C1. If I can prove this, that means it is a path function. So for cycle 1, this is the thing 1A 2B1. For cycle 2, this is the thing 1A 2C1. If I apply first law of thermodynamics to cycle 1, then I can write summation of Q equal to summation of W. For cycle 1, I can write net heat 1A2 plus 2B1 equal to work transfer for 1A2 and 2B1. This is from the first law of thermodynamics we can write. Similarly for cycle 2, we can write from the first law that 1A2 plus 2C1 heat transfer will be equal to 1A2 plus 2C1 work transfer. So if I subtract this equation 2 minus equation 1, then I will get the work transfer is also not same, along with the heat transfer also not same. From that point we can tell that work transfer and heat transfer both are path functions, as for this curve and this curve the heat transfer and work transfer are different things. Okay, so the conclusions for heat and work are path function, and heat and work are these are not a property. If these are a property, it is a point function, but these are not property. Again I am telling you, I will discuss in the later stage, these heat and work are transient function. Why I am telling these are transient function is, these work transfer and heat transfer W and Q, sometimes they behave as a property, sometimes they behave as a point function. That's why we call it as transient function. But the origin is these are all path functions generally, and these are also inexact differentials, and these are boundary functions. Next, coming to if not a cyclic process. So for cyclic process, the first law of thermodynamics we have defined summation of Q equal to summation of W. But if not a cyclic process, then what will happen? Summation of Q will not be equal to summation of W. That means there is something extra. If added to the work transfer, it will be equivalent to heat transfer. So dq equal to dW plus du, which we define as an extra quantity, has to be added with the work transfer, then it will be equivalent to the heat transfer. This du we defined as an internal energy, which is a property. So from the first law of consequences we defined a property that is named as internal energy, and this statement, this dq equal to dW plus du, is valid for both cyclic and non-cyclic process, but it has to be for closed system only. Next, coming to the first law for any process, both for reversible and irreversible, I have derived that one. I have discussed that one in the previous one. So dq equal to dw plus du. So this is now our first law consequences, okay, for reversible and irreversible. Next, for adiabatic process, we know the heat transfer is 0. If for an adiabatic process the heat transfer is 0, then from the first law dq equal to dw plus du. If this is 0, then dw I can write equal to minus of du, or dw mod equal to du. That means d work transfer will be equal to the internal energy change. But I have already told you this internal energy change is a property. So work will behave as a property, but it is a path function, we know that, but it will behave as a property. So sometimes it behaves as a property, that's why we call it as transient function, okay. Likewise in isochoric process, what is there? Work transfer is 0, w equal to change in work transfer is 0. So dq equal to dw plus du from the first law, this is first law. So dw is 0, dq equal to du, then q will behave as a property. So we can tell q is also a transient function as it behaves as a property sometimes, like in isochoric process. So from the first law of thermodynamics we defined one property, that is internal energy, okay. Next, coming to the energy part. What is internal energy? So the total energy is the summation of potential energy, kinetic energy and internal energy, okay. But for gases we can neglect the potential energy and kinetic energy. So internal energy is taken into consideration because potential energy and kinetic energy are very less than internal energy. That's why we take internal energy into consideration for gases, as we discuss gases mostly in thermodynamics. Next, what is internal energy? Internal energy, the energy associated with the system at molecular level, is referred as internal energy. That means in molecular level, whatever energy contained by the molecule is named as internal energy. It depends upon the molecular properties like molecular weight, molecular structure, temperature. We know that there is a crystal structure in each and every molecular structure, okay. So they are having some molecular weight, molecular structure and temperature. If molecular weight is going to change, the crystal structure will change. If temperature is changing, the crystal structure will change. That's why the internal energy depends on the molecular weight, molecular structure and temperature. This is internal energy. But the major formula we use for internal energy is mCv/dt. It is, I have already told you that all types of energy are extensive property because all types of energy are dependent on mass. Here also in internal energy case we can see that the formula is mCv/dt, where Cv is the coefficient of specific heat at constant volume. So the change in internal energy equal to mCv/dt. As you can see, the change in internal energy is directly proportional to the temperature difference. So increasing the temperature difference, the internal energy change is going to increase. Next is internal energy per unit mass. If we divide the internal energy formula, that is mCv/dt divided by m, then we will get only Cv/dt. Then it will behave as an intensive property. That means extensive property is U divided by m. It will be a intensive property. Okay. Next, for an isolated system, what is the value of internal energy? For an isolated system, there is no mass transfer, there is no energy interactions also. So there is no mass transfer, there is no heat transfer, there is no work transfer. So from the first law we can write dq equal to dw plus du, but these are 0, then du will be 0. So U will be constant. That means the initial internal energy will be equal to the final internal energy. Next, coming to the limitations of first law of thermodynamics is PMM1. PMM1 means perpetual motion machine 1. PMM1 tells us that without any energy input I can give work, but that is impossible. So without any energy input work is done, which is an impossible. So this device is impossible. We cannot make this device. Without any energy input we cannot get some work done. That's why this is impossible. Next, coming to the enthalpy. So enthalpy also an heat energy. Enthalpy is nothing but one kind of energy which is defined as H equal to U plus PV. This is a very important formula. H equal to U plus PV. Okay. So where S is the enthalpy, U is the internal energy, P is the pressure, V is the volume. Okay. So this is the definitions of enthalpy, that is summation of internal energy and the multiplication of pressure and volume. Next, coming to the formula of change in enthalpy. A change in enthalpy is defined at a constant pressure. That's why we tell the change in enthalpy formula is mCpdT, and Cp is the heat at specific heat at constant pressure, and dt is the change in temperature. Like internal energy, change in enthalpy also dependent on the change in temperature. So if we increase the temperature change, the enthalpy will also increase. So we know that H equal to U plus PV. We already defined that in the enthalpy case. So if we differentiate both sides, then we will get dH equal to du plus PdV plus BdP. But PdV is the work done we have already defined in the last lecture. So if I replace PdV by dW, then du plus dW plus BdP. Again from the first law we have defined that dq equal to dW plus du. So if I replace this with dq, then I will get dH equal to dq plus BdP. Okay. Next, a general thing, can you prove Cp minus Cv equal to R? Okay. In the previous one we discussed H equal to U plus PV. Okay. So if I will take, it is an ideal gas. For ideal gas it is generally defined. If I take this, and then from the ideal gas equation we know PV equal to mRT. So if I replace H equal to U plus mRT, it is okay. Next, we know that H equal to mCp delta T, and U also we know mCv delta T, and mRT I am writing like, if I differentiate mR delta T. Okay. So I have replaced everything in delta T form. That means if I replace this dH here, dH du dt, if I differentiate both the sides, I will get this. If I replace dH, then I will get mCp dt. If I replace du, mCp delta T. If I replace mR dt, then I can replace dt and delta T are same. This is also represents change, this is also represents change. Okay, you should not be confused with this. Next, if I divide everywhere m delta T, then I will get here I will get Cp minus Cv equal to R. I have derived this. Next one thing, for air, I have already told you that air in the first lecture, I have told you air can be dealt as an ideal gas. So the Cp, Cv and R value of air should be remembered. The Cp for air is 1.005 kilojoule per kg Kelvin. Cv is 0.718 kilojoule per kg Kelvin. R is 0.287 kilojoule per kg Kelvin. And last gamma, in this is the coefficient of adiabatic process, it is also 1.4 for air. These are defined for air. Okay. Next, coming to the heat transfer for various processes. So heat transfer for various processes, first process is isochoric process or constant volume process. Okay, for constant volume process we know dW equal to 0, so dQ equal to du, that is equal to mCv dt. This is the graphical representation for isochoric process. If pressure is increasing but volume is constant, right, for constant volume process or isochoric process, if it is in upward direction then heat addition takes place, if it is in downward direction then heat rejection takes place. Next, coming to the constant pressure process. In case of constant process, if it is in this direction then heat addition takes place, if the volume is increasing heat addition takes place, if the volume is decreasing then heat rejection takes place. So what will be the value is dQ equal to du plus dW, and we know dW is pdV, so du plus pdV, but again we know H equal to U plus PV, so dH will be du plus pdV plus VdP, but pressure is constant, so this term will be 0. Then we can write dH equal to du plus pdV, which is nothing but dQ, and we know dH formula is mCp dt, so we can write dQ equal to mCp delta T. Okay, so this is the heat transfer for isobaric process, which is a constant pressure process. Next, for isothermal process. For isothermal process is the temperature initial and final temperature are same, so du will be 0 because it is mCv delta T, it will be 0, so dQ will be equal to dW, which is pdV. Okay, for adiabatic process, and these are the curves I have already discussed when I discussed the work transfer or work energy interactions. Okay, these are the PV diagram for isothermal process, this is the PV diagram for isobaric process. So what will be the heat transfer in case of adiabatic process? Sorry, this is the curve for adiabatic process. So the heat transfer for adiabatic process is 0, we have already know this. Okay, and the equation is PV to the power gamma equal to constant. Next, coming to the polytropic process, the equation for the polytropic process, we know that PV to the power n equal to constant. From the first law of thermodynamics, we can write dQ for polytropic process equal to du plus dW for polytropic process. So we know that du equal to mCv delta T, and for polytropic process the work done I have defined in the last class, that is P1 V1 minus P2 V2 divided by n minus 1. But we know that Cv equal to R by gamma minus 1. So if I replace R by gamma minus 1 in place of Cv, mCv dt will be m into R by gamma minus 1 into dt. So m or dt I can write P2 V2 minus P1 V1 divided by gamma minus 1. So in place of du we can write P2 V2 minus P1 V1 divided by gamma minus 1, and for dW for polytropic process, that is P1 V1 minus P2 V2 divided by n minus 1. If I take the LCM and I get the final expression like this. For polytropic process, the heat transfer will be P1 V1 minus P2 V2 whole into gamma minus n divided by gamma minus 1 into n minus 1. So this formula is used for the heat transfer of polytropic process. Again, in the first we have defined the definition for the heat transfer, that is mCp delta T, right. If I write for Q polytropic process mCp delta T, mC polytropic process into delta T, it will be equal to this. Then if I get the polytropic specific heat, then this will be like this. So n minus gamma will be negative because n is less than gamma, it is always, and gamma is greater than 1, n is also greater than 1. So for this, the net expression for polytropic specific heat will be negative. So if the polytropic specific heat is negative, then if we supply the heat transfer into the system, then there will be reduction in temperature. Why? Suppose this is a system, we supply the heat, but heat is mCp delta T, right, or mC delta T I can say. So the heat transfer is mCp delta T, right. So for this process Cp is negative. So for the heat transfer we know that Q equal to mC delta T. So if C will be negative, then in place of mC T2 minus T1, it will be mC T1 minus T2. So in place of increasing the temperature, it will decrease the temperature. So to accommodate that, in polytropic process we tell that work done must be larger than heat transfer. So next, coming to a good question, a gas of mass 1.5 kg undergoes a reversible process, follows the relationship P equal to A plus B into V, where A and B are constants, P in kilopascal and V in meter cube. Initial and final pressure are 1000 kilopascal and 200 kilopascal. Corresponding volumes are 0.2 meter cube and 1.2 meter cube respectively. The specific internal energy has given in a function of pressure and volume, that is 1.5 pressure into volume minus 85 in kilojoule per kg, where P in kilopascal and V in meter cube per kg. Calculate the heat transfer and maximum internal energy for the gas. So if I represent the whole question in graphical format, this will be the curve. It will be a straight line of downward slope. It cannot be in upward slope. This is the line. This cannot be like this, because at 1000 kilopascal that will be 0.2 meter cube, and at 200 kilopascal it is 1.2 meter cube. Okay, so this has to be the curve. Next, in the question it has been given P equal to A plus BV. So at 1000 kilopascal it is 0.2 meter cube. I get one equation. Another equation from 200 kilopascal. From that I can calculate the values of A and B. After calculating the values of A and B, you can calculate the work done from the pressure and volume diagram. As we know, the work done is nothing but the area under the pressure and volume diagram. So if you calculate the work done, it will be the area of the PV diagram. That means this was the work done. Okay, so half into 800 into into 1.2 minus 0.2 plus 200 into 1.2 minus 0.2. If you calculate this, you will get it as 600 kilojoule. So if you calculate the net heat transfer, for that you need internal energy change. So if you calculate the dU, it will be 1.5 P1 V1 minus 85 minus 1.5 P2 V2 plus 85, then you will get the net change in internal energy at 60 kilojoule. So the net heat transfer will be dq equal to dw plus du, that will be 600 plus 60, it will be 660 kilojoule. Okay. Next, coming to the maximum internal energy, I am giving a hint for that. So the maximum internal energy, this should be du by dv equal to 0. Okay, for du by dv equal to 0, in that case u will be u max. So you know the value of u is 1.5 pv minus 85, right? So put p value a plus bv, you know a and b, put over here, and you can differentiate with respect to specific volume, you will get, and equal to 0, you will get the maximum internal energy. Please try this and give the answer in the comments. Okay, I have calculated the first part, that is net change in heat transfer. You calculate the maximum internal energy. I am giving the answer u max equal to 503.25 kilojoule at specific volume or volume of 0.725 meter cube. This is the volume, not specific volume, at 0.725 meter cube. This is the answer. Okay, you calculate it and tell me in the comment what values you are getting. Next, coming to a important portion, that is diffusion of gas. Suppose this is one chamber, this is another chamber. The pressure, volume, temperature at the respective chambers are given. After mixing or after diffusion, when the partition between two chambers are removed, okay, then can you calculate the final pressure, volume and temperature? So for this, what I will do, I will apply directly, you know the volume, right? V3 equal to V1 plus V2. These two chamber, if the partition is removed, then V1 plus V2 will be the final volume, that is V3. So from conservation of mass, you know m equal to m1 plus m2, that means m3 equal to m1 plus m2, that is p3 v3 by t3 equal to p1 v1 by t1 plus p2 v2 by t2. This is the thing. Okay, and from conservation of energy, as this is an isolated system and this one is also an isolated system, when the partition is removed, u of initial will be u of final, internal energy will remain same, that means u3 equal to u1 plus u2. So I can write CVT3 will be equal to CVT1 plus CVT2. Then you will get, as this is CVT3 or M3 CVT3, M1 CVT1, M2 CVT2. So M3 can be represented as M1 plus M2 into T3, that is equal to M1 into T1 plus M2 into T2. So this I can write as P3 T3 as PV equal to MRT. I can write P3V3 is M3R T3. So R will get cancelled everywhere, P1 V1 plus P2 V2. Okay. Then if you from conservation of mass you get one equation, this one, and from conservation of energy you get these equations. So the final equations you will get is the P3 will be P1 V1 plus P2 V2 divided by V1 plus V2. From this equation only you get this, from equation number 2, and T3 will be P1 V1 plus P2 V2 divided by P1 V1 by T1 plus P2 V2 by T2. This is another final temperature expression for diffusion of gases. Okay, you can get it. So next important point is, for a cyclic process, change in property is 0. I am taking one example of property, that is internal energy. From the PV diagram I have shown here, 1A2 is the forward process, 2B1 is the backward process, and it is completing a cyclic. It is started from 1 and again ends at 1. So this is a cyclic process. As you know, internal energy is in point function. That means it only depends on the initial and final points. So for this path and this path, the internal energy will be same. That's why U1A2 will be equal to U2B1. So for this cyclic process, change in property, that is delta U, change in internal energy, will be 0. Any property you take for cyclic process, any property, the change will be 0. Next, coming to the free expansion. So free expansion is an important concept in thermodynamics for which work is not required. Expansion of a gas against vacuum is known as free expansion. That means if a system is present inside a vacuum and it is releasing the gas and it is expanding in this vacuum chamber, named as free expansion. It is an irreversible process. We cannot gain back the forward process. That's why we tell it as irreversible process. Once the gas is leaked into the vacuum, we cannot gain back the gas into the chamber again. There is no resistance in vacuum, that's why there is no work done, so work done will be 0. And as it is occurring in isolated system, we call Q will be 0. It is an isolated system. Okay, so as the free expansion always occurs in isolated system, so the net heat transfer will also be 0. The work transfer is 0, the heat transfer is also 0. So from the first law of thermodynamics, we know for free expansion dq equal to du plus dw. As dq is 0, dw is 0, then du will also be 0. That means u is equal to mCV_T. So U1 will be written as CVT1, U2 will be written as CVT2, CV will get cancelled, it will be T1 equal to T2. If the temperature is same constant throughout the process, it is named as isothermal process. So the free expansion process will behave as an isothermal process. Okay. Next, coming to the curve. If I am telling this is an TV diagram, okay, so for this TV diagram, 1 to 2 is an isothermal process and 1 to 2 in this path will be free expansion. It is similar to isothermal process, but it is not the actual isothermal process. So in case of free expansion, it is similar. The temperature, initial and final temperature is same. So in case of isothermal process, temperature remains constant throughout the process, but in case of pre-expansion, temperature initially decreases, then it increases, it meets at the final temperature. So initial and final temperature will be same. So this is the end of the first law of thermodynamics process. Next we will discuss the steady flow energy equation, which is the application of first law.